Okay, I still prefer to give now our talk in English language because we have a few only English-speaking friends, attendees of our seminar. So everything is clear about our seminar and about the dedication. This is a fine calculation I have made when preparing our talk. I decided, and we decided with Dong to choose a very popular topic. This is a normal distribution. Everybody knows, loves, works on this, using this. And now I hope that you will meet at something which is not so well known. So we are using standard modern notations and terminology. One glance is enough. I don't need to read it. What is this? Because you know this better than me. So MK will be the notation for the moment of order K, assuming at some integrability or summability. So this is our main standard normal random variable Z. And this is the notation. And the absolute value of this will be half normal. So this is the density, the distribution function. So this is phi. So, and this is phi. In Greece, this is the pronunciation of the letter phi, not phi, like the Americans say. So we have this. We will be using also two functions. One is the moment generating function, and this line, characteristic function, and cumulative generating function, the logarithm of this. Now, I'm not going to talk about some examples and counterexamples. Everybody has his or her own repertoire. And there is something new, including a very interesting construction. It is easy in a recent paper which appeared in TPA just 3 years ago. It's Max Janisch, the youngest author of a paper in the journal Theory of Probability and Applications. We will be talking also about the infinite divisibility, a property which is quite important for limit theorems, if you are doing some work in Levy processes. And we can consider this in terms of all the X, F, another F, characteristic function, etc. Some good attention today, we will pay to our favorite topic or subtopic, moment determinacy of distributions. It's a great story. So first to remind that here there is the so-called dichotomy. This is how the word, that it's a Latin word, dichotomy, that if you have a random variable distribution, all moments finite, then there are two possibilities. Either uniqueness or M determinate, or non-uniqueness M indeterminate. And here are some names, etc. And since we are working with Dong on this topic for more than, let me remember, maybe more than 20 years. Yes, maybe near 25 years. We have some 10 joint papers. Each one of us has his other papers. And so we are giving talks very frequently on this. And because of this, our opinion is that many of the results in this area, they are at least slightly known. However, we still believe that there are results which are not so well known. And here is a list. Kramer, existence of the moment generating function, like tell it, all moments finite, we have uniqueness. Quite popular Kahneman condition, which is depending on the support, the whole real line or the positive, we write this sum or this sum, and if this sum is infinity, then we have uniqueness. It's a very useful, sufficient condition for the uniqueness, for the moment determinacy. And now the next is, it's called Crane. So because it's an absolutely continuous case, there is a density, positive, the logarithmic function to be well defined. And in the two cases, we define this in two different ways, this and this. And now if this integral is finite, we have non-uniqueness, or M in that, moment indeterminate. Then the next is called Hardy. We have positive random variables. Square root is well defined. Now we require Cramer condition, moment generating function, for the square root of x. It's written here. And if this is satisfied, then x itself is unique. By words that f is the only distribution function with this moment sequence. And now here we have a good development. And in the literature, this is called the Crane-Lin conditions or Crane-Lin technique or techniques. You remember in the Crane condition here, this is the classical Crane condition, 1944. Then here's 61, and then some other guys. And now, what will happen? This is the question. What will happen if we have the inverse Crane? So the integral is not finite. The integral is infinity. So under some small conditions, but now we involve a condition which already for more than 20 years adopted the name Lin's condition, because my co-author and friend Godong Lin was the lucky man to invent this condition and to prove the following result. If Crane is infinity and this condition L is satisfied, then we have uniqueness. There are some small extensions. I put here some references. And something else which looks easy, however, it is very convenient for people in applications. And so there are several applied statisticians contacted me and asking, oh, we have data, we can calculate this and that, etc. And I'm confirming if I'm happy with their conclusion. So now we introduce what is called rate of growth of the moments ratio. So this is the ratio in this case, this is the ratio in this case. And here we have some delta. And it turns out that all depends on this delta. So we have three statements. So if delta is not more than 2, we have uniqueness. Delta equal 2 is on the boundary, on the border. It is very, but this is the best possible constant. We have very tricky counterexample. And interesting, if delta is more than 2 and condition L is satisfied, then we have non-uniqueness. And again, there are some papers, etc. So what is important to recall is a fundamental theorem. So this is Berg, is Christian Berg and company in Copenhagen, Denmark. If a distribution function with finite moments is non-unique, then there are infinitely many of any kind, absolutely continuous, and infinitely many purely discrete. They all have the same moments as f. One possibility to, however, Berg and company, they didn't advise how to construct such infinite families, for example, around the center, around this. One possibility was to introduce the so-called Stiltes class. And I have done this some 20 years ago, and it turns out that this notion is quite useful. Now, several people, when having a distribution with finite moments, non-unique, they try to construct Stiltes classes by following something from the machinery that we have developed. And even there are some new approaches. For example, Lopez Garcia from Mexico City, he tried to use what is called a Hilbert transform, and he succeeded to do it. He has very nice publication. And these are two American authors, and they used some methods from quantum theory, which is a very funny story. And now a little more, just to refresh our memory, the standard normal Z. These are the moments. These are zeros. These are 2k double factorial. We know the story with Chebyshev and Markov. The second half of 19th century, when they proved the central limit theorem for arbitrary sequence of independent random variables. So the first factor doesn't need even explanation, that the normal distribution itself is unique or m dead. Even there are several kinds of arguments. Now, the next more interesting is to consider the so-called Box-Cox transformations, either integer powers, integer positive, or real powers, we take the absolute value. And it turns out that here there was what to do, and here is a very short but funny episode. This happened when I was a student at Moscow University, and I met once at Albert Shiryaev randomly. It was in MU, in the Moscow State University. And so he asked me promptly, because he saw me maybe a little bit disturbed, and he asked me, what are you so occupied with? And I told him that, look, I'm reading the book by Prokhorov and Rozanov, Theory of Probability in Russian. And I stopped at the following statement: the cube of a normal random variable is non-uniquely determined by its moments. So at that time, I was still a student, and maybe still not knowing it so much. However, Albert Shiryaev told me the following very wise words: one day, Dancho, you will understand this and more, and explain all the details to us. And in fact, I'm very glad to report that to our teacher, Albert Shiryaev, that I'm doing this, and I believe essentially more, for the many years after I graduated from Moscow University. And now let us go to these integer powers, 2, 3, and 4, and then real powers, these. For example, such a fact that the square is unique, the power 4 is unique, and we have enough machinery to prove any one of these statements, and even a little bit more. Be corrected, and this we published at the Godon Clean, that there was a small, incorrect statement in the book by Prokhorov and Rozanov. And this is about the power 4 of Z, of the standard normal. And I used the opportunity when Professor Prokhorov was still alive, and I met him at the Steklov Institute. It was a good chance because he was not coming so frequently. And I showed to him, okay, let us take your book, and now let us see one of our papers, and also my book. And it is well justified, also all is correct, that power 4 is unique. Of course, Prokhorov is a man with good life experience. And after maybe 10, 15 seconds, he told me the following: now I remember that responsible for that part of the book was Rozanov. Okay, I only smiled, and then we continued. And as we usually try, together with Godon Klein, to tell that to apply twice Cramer condition and twice Hardy condition is the shortest and the most elegant way to prove the power 4 of the normal is unique. And now we have a quite easy statement, because we really have the tools how to check that a specific distribution, especially if there is a density, we can do. However, here there is something which is quite unusual. So we know already that the power 3 is non-unique and in that. And it turns out that you take the absolute value, and it is becoming m that. And when giving talks, people were stopping me and telling, no, it cannot be. But how this does happen? Okay, now, and here I have at least 2 different proofs. So this is the density of the cube. So capital X is this, and this is absolute value. So this is twice this density. Now we just make calculations. So we know these moments. So we calculated you remember delta was the rate of growth of the moments ratio. It's more than 2. Okay, then we have non-uniqueness. Now for the absolute value, we have this moment of order k expressed in terms of gamma function, and the growth rate is 3 over 2, which is less than 2. We make the conclusion that x is unique, and we can sleep well. And now a few words about a very simple and natural operation. This is products of independent random variables. So we have series, a few papers, and some other people also did a good job on this. And I decided not to tell about general results, but to see how these results apply in our favorite normal case. So if we take the sequence of, we have a collection of independent, normally distributed, the parameters is not important. Then the product of any two is unique. However, the product of any three or larger number is non-unique, M indeterminate. And then we have a similar fact, already factor number 5, for half normal. And you can see, is there some question? Because somebody is бормочет. Нет, хорошо. When talking about products of half normals, so we have everything is unique for 2, for 3, for 4, but starting from 5, so this is the first n equal 5, we have already non-unique and any larger number. And here I listed for you to satisfy perhaps my own and also your curiosity. What will happen if you start mixing? You take one of these. For example, you take an inverse Gaussian.
Sorry, what is IG? IG, what is IG? IG class.
IG is inverse Gaussian.
Oh, inverse Gaussian. Thank you.
It was Sergey, it was at the very beginning, inverse Gaussian, but there will be something more later. Don't worry. It's a good, interesting distribution. And then if you take this, if you take this, if you take this, and what is even funny, so this question came from Anirban Dasgupta from Purdue University, and he asked us once, oh, Jordan, but what will happen if you take the normal random variable in power integer valued non-negative random variable? Okay, we always have, there is one case. If you, but I will not spend it my time. Now here there are two open questions and one curious statement. It is about the infinite divisibility. So we know that Z itself is infinitely divisible. I have known for several years that any odd integer positive power of Z is also infinitely divisible. And then when preparing the talk, and we discussed with Godon Lin, and we didn't find this immediately. However, our friend at Simon or Tom Simon from University of Lille, he promptly gave to us the right reference. This is Bondesson, 1992. So now what we are doing here, so this is the Stiltes class. Now, this G is the density we know, and this H is the perturbation function. It's a periodic function. We found exactly this one. And now we are interested what is happening with the elements of this Stiltes class, because epsilon is running between -1 and 1. Epsilon equals 0 is not interesting. And now the first open question, sorry, it's number 2. Is it true that X epsilon, for epsilon not 0, is not infinitely divisible? And my conjecture is yes. I have some arguments, but not the complete proof. And then another good question is, knowing that power 3 is non-unique, but it is absolutely continuous. Okay, how to find purely discrete random variable with the same moments? And here's the next open question. So how to find discrete random variables? So we are looking for two sets, D, these are real numbers, ordered set, and P, probability distribution over these, such that the following system is satisfied. So all odd order moment to be 0, and all even order to be this. So what we have is we run K, so we have infinitely many equations. However, we have twice more unknowns because we don't know these numbers and we don't know these numbers. And I have to admit, and I will be, so what we know is that from the Berg fundamental result that there are infinitely many solutions. And your speakers today, it's me and Dong, we don't know any. I will be happy if somebody gets such a discrete random variable. I know what to do with this. I will cite you. I will make you very famous. I know how to do this. And here is a small procedure, how from continuous, by using discretization to produce a discrete random variable, such that, so we have to check it, the so-called Pedersen condition. Pedersen is one of the former students of Berg in Copenhagen. So this is analog of the classical Crane condition. So now we have only this approximately, a little bit below, a little bit after, but not exactly. And so we can exploit also the other random variables, z squared, and z power 4, which are unique. And I think there is somebody keeping the microphone on, because I'm hearing some echo. Okay, let me continue. This is the statement. Show that there is no solution to any of this system. Look at here, there is one system. Here there is another one, and here there is another one. And I'm claiming that these systems do not have solution, and the solution is based on probabilistic arguments, because we know what is z squared, and z power 4. And I even suggested to some people in analysis, say some cash reward or a bottle of wine, if they find the solution without using our probabilistic arguments. No success yet. And now I will tell you about another quite interesting result, which was published a few years ago by Konstantin Lykov. I'm wondering, Kostya, are you listening?
Йордан,
Lykov is presently in me.
Слышу.
Ага, хорошо, да. So now I call this unusual decomposition. So now we have a random variable with finite all moments. We don't know anything more. And it turns out that this random variable x can be decomposed or represented as the sum of two random variables, x1 and x2. Each one, so this and this, satisfies Kalman condition, which means that separately x1 and x2 are unique. It's really a little bit unusual, but he has done it, and his paper is in TPA a few years ago. And now I will show, this basically is from his paper, but in our reduction, our presentation. So this is the density. So we take some two integer sequences, xk and qk. We use xk in order to decompose R. So this is, so we take in some intervals are on the left, the other symmetric is on the right, and you can see. And then the other R2 is the complement. And now we use our density F. We define first this function F1 and this F2, and then we take additional normalizing constants, and we produce two new probability densities, G1 and G2. And of course, we can do some similar work and see that the sample space, capital omega, is the sum of the union of this and this. So we have this sum, and then it is quite a delicate analysis. So we followed at what is in the paper by Leikov, but the idea is the following: we bound first the moment of order qk of the random variable x1. So we go. I didn't write the details because we have to succeed. We have a limited time. Our boss, Lena, is giving it 45 and 49 minutes to me.
Of course.
And now, so this is how we show Kármán condition for x1, the same way for x2. And this means that we indeed have a random variable x for which we don't know anything. However, we have this very nice, funny, attractive decomposition. Now something about the log normal and its moment determinacy. So this is the definition. This is the density everybody knows. It's heavy tail, no moment generating function. However, we can calculate, surprisingly, the moments. Look at the very beautiful expression. And now I will write two classes, which I call Stiltes classes. One is continuous, one is discrete. In fact, here we have in the continuous case, we have the family of random variables and the family of densities. Here we have the family of random variables, and here we have the family of the probability distributions. So we use very intensively F, and then we use, of course, some analysis in order to show this property, which I will mention just in a moment. One name. I'm not the person who invented the name shocking property. However, now if for this, let me return back. If for this x epsilon, the density f epsilon, we calculate the moment of order k, it turns out we find this. We take ya, here a is running any real number. Here we have integration, here we have summation, and we get the same number. And here is another episode that when some years ago I was visiting at our good friend and colleague at Nikolai Krylov at Minnesota, and I was giving a talk, of course. And when arriving exactly at this place about the log normal, and so now Professor Krylov asked to stop for a moment by telling more or less exactly the words. It is shocking. I never thought it was possible. So different distribution to have the same moments. So he announced the break, and he went out and he smoked a cigarette. Then he returned back and thought, okay, life is full of surprises, but it's good to know it. And he told me, thank you, Dan, for telling us. And now we have something else also involving the normal distribution, something which I liked it very much. It is based on the paper by Joseph Pinelis at an archive. And, I didn't find another, but it seems that Joseph confirmed that there was no real publication in a journal. So he called this exponential normal. So we take z, we know what is z, absolute value, and logarithm. And this we easily calculate the density. Sure. The values are on the holy line. And this is the relation between z and this, epsilon plus minus 1, a Rademacher random variable, independent from everything else. And now the question about so what we know is that the normal distribution is infinitely divisible. And the question which Pinelis discussed in this, it's a short paper, but nice, is about the infinite divisibility of the exponential normal. And here is one of his results. I have given here the result in a little bit in another order. This is the order which I like more. So first, at the and he showed that the random variable u, the logarithm of absolute value z, has this representation. Okay, there is some constant, forget. And all these random variables with tilde, these are centered exponential. And because the exponential is infinitely divisible, then we have linear combination, it doesn't matter. We have convergent series, etc. So this is as a consequence, we conclude that exponential normal distribution is infinitely divisible. So you can see the details in the paper by Pinellis. And so it is quite difficult result that the log normal distribution is infinitely divisible. And as I knew this from Bondesson himself, the name of Thorin, etc. But now I want to involve another property. So log n, you remember the density. It is very nice that I didn't include it here graph, but it is unimodal. The density has only one maximum. And now I'm asking the next open question. So when telling open question, this means that the question is open to me. Maybe somebody else knows the answer or will find the answer. I will be very happy if somebody is so lucky to share this knowledge with me. And first, about the stilted class. So let us we take epsilon not 0. And my conjecture is that x epsilon and f epsilon is not infinitely divisible. And only then we go to the next open question, which is here number 5. Now assume that we start with an unknown absolutely continuous distribution function on R plus, finite all moments, unimodal density, and suppose that we know explicitly the moments. And we are asking, under these assumptions, is it true that there is only one distribution f, and this is exactly the log n? I don't have the answer. I don't have a conjecture. However, there are some people who liked the question. One of them was Ildar Ibragimov at St. Petersburg a couple of years. Sorry, it was just the year before COVID. And he liked this, but no any progress reported yet. Now, quite popular are distributions which involve the normal or the log normal. So here you can see the notations and even the definitions that we don't need it too much, because one glance is enough to refresh the memory and to know what is skew normal and what is log skew normal distribution. And now we are asking about the properties of these two, skew normal and log skew normal. And I will provide here only one result, which is from one of our papers with Gordon Klein. I think it's, yeah, okay, to the general applied probability. And so you see the notation with Z, this, and absolute value of Z half normal. So there are two claims. Now, what we see here is that everything depends on lambda, and lambda is running from minus infinity to plus infinity. And now we can ask what is happening if lambda goes to plus infinity, and separately, what happens if lambda is going to minus infinity. And it turns out the pictures are quite different. If lambda goes to plus infinity, then we have a very heavy tail distribution, we have non-uniqueness. However, if lambda goes to minus infinity, look at, we are getting a bounded random variable. So this, some people know this and some people don't, but now from our presentation today, you have a chance to remember this and to use and to tell to somebody else. Now something about the IG, the inverse Gaussian. I'm sorry, I didn't maybe introduce the definition properly before, but I think everybody knows that IG is this, what is given here with two parameters, mu and lambda. And even I will not give this very general result. I will go directly to the particular case of 1, 1. The parameters are mu is 1, lambda is 1. So this is the density. Look at the very beautiful function. It is 0 for x less or equal 0. I didn't write here. And now, what we know and what we have established is that power 3 of the Ig random variable, any, including this one, with 1, parameters 1, 1, is power 3 is non-unique. So in that. So this is the density of power 3. Now, capital X is our C power 3. So this is the density. This is the function perturbing the density in order to write this Stiltes class. Sorry. So we write the Stiltes class as before. Now epsilon is running from -1, 1. And now we can ask it questions similar to those as we have done before. Now let us exclude the case when epsilon is 0. So the center is still good because it is infinitely divisible. However, the claim is that x epsilon and f epsilon, if epsilon is not 0, are already not infinitely divisible. And as before, we are asking how to construct a purely discrete random variable. From Berg, we know that there are infinitely many. And once again, maybe it is a shame to tell, but I don't know anyone. I'm trying to get some. And now we return back to the end of 60s when Albert Schreyer was running a seminar at the Stekov Institute, seminar for his master students, Alex Novikov, Alex Zvonkin, Volodya Lebedev, Zarek Maimin, Fima Fried, and I was there, Andrei Salem, and was maybe one more. And Albert Schreyer suggested to us the following very tricky question. So first we started with the relatively easy statement that the linear transformation of a normal random vector is always going into a normal random vector or random variable. In this case, a three-dimensional vector to one-dimensional normal random variable. And of course, we tried, etc. We have done this. Then a little bit later, when I was already in Sofia, Bulgaria, I was working at the academy. I was teaching at Sofia University. And together with my colleagues, we prepared a book, which is called Exercise Manual in Probability Theory. And in the very first edition, we included this as, this is number 1636. It is also included into the well-known collection of problems by Zubkov, Sebastianov, I think Chistyakov maybe. This is the second edition, 89. It is this. And also there is a book by Shiryaev, Yerlich, and Yaskov. It is also one of the exercises there. And now what I want to show to you a new proof of the normality of the random. So this was the nonlinear transformation of three-dimensional Gauss, normal vector. Maybe I will go a little bit faster because I'm trying to see the time because I have something more to tell you. So in two steps. So now what we the first step is to check that odd order moments of t. So this is t. The odd order moments are all 0, and it is true. Okay, this is the conclusion. And now, but here there is one useful observation, because t itself, we can see is okay, it is unique. And if unique and the odd order moments are zeros, then t is symmetric on the whole real line. Because if it is not unique, then sorry, it is not necessarily symmetric. And now step 2, we calculate it step by step. So we have this and Newton binomial formula, and then some integral, And it was a funny story, and finally we arrived at this. But this is exactly what we need. But the conclusion is here. I would like you to understand why I have included this. There is a moral. If we have two random variables, and we know the moments, and the moments of one are equal to the moments of the others, and then in the case of uniqueness, the distributions are the same. And quite interesting additional results are included in a paper by Linda Khachatyan and Boris Nakapetyan. So it's quite recently. It's Armenian Journal of Mathematics, with all the details. And now here there is another property which in the literature is called Shep property and normality. So Shep published a problem in Siam Review. So 64, maybe 62, 64, the solutions. And it is the following. In fact, I have given this in my own words, because here there is an interesting observation, the paper by Linnik and Eidelman in Theory of Probability, about the behavior of a function if we want to keep the normality. So the function h must be linear. It's quite tricky, but all these are useful results. And now what I have to tell, several people work on this, maybe this direction. I like the
Можно
book by Sergei
простите,
Novak.
можно сделать одно замечание? А вот этот результат Шепа был независимо получен примерно в то же время Зингером, Абрамом Ароновичем.
Okay, very good. Thank you very much, Lev, for the reference. I will look at this, and then if and when necessary, I will tell it. But is the result of Zinger exactly what I'm showing now with my mouse? In both directions. So if this is normal, then we have normal. If this and this are normal, then this is normal. Okay, I will check it. Thank you very much. So these are the authors, and this is a quite interesting paper by Dasgupta and Shep. And I like that what Novak did. He showed that this coefficient 2 cannot be changed. You change 2, and you have another. There is a beautiful counterexample, which maybe I can buy it from him. And here there is an episode because, as you know, I'm a person traveling a lot in the world, and I got the chance to meet Larry Shep 1 year before his unfortunate death. And when I met him at his office, University of Pennsylvania, so he welcomed me, and he told me, Jordan, I like counterexamples, I like the normal distribution, I like the moments. Let us talk. And so we had an excellent, he knew about all these papers. He has visited Steklov Institute at approximately the years. Some conversation with Linnik, Shiryaev. He knew about Novak, and he liked my suggestion to talk about, maybe after the comment coming from Lev Klebanov, we call this Shep, Novak, Zinger, Veselovsky, and somebody else. Now, one step more. Shep also suggested that this is another nonlinear function now I'm showing. I tried to find in the literature if there is a converse, and I didn't find. And because of this, I decided to formulate this as an open question 6. If the answer is yes, then we will have another characterization property. I don't know. And now, once again, something about the normal. So it's a result which, so the result I'm showing now is classical, and you can see this in hundreds of books and papers. And as our friend, Dasgupta suggested, Jordan, it is time now everybody to discard this poor form of the statement and to use another improved bound, which is here. So after working for maybe some 1.5, 2 years. So we managed to show, so this is the classic. But what is different between this and the previous one? So the previous one is asymptotic, but our is for any fixed n, maybe more than 7, maybe 10 or something like this. But we know explicitly look at this term, and then we know the length of the interval between the minimum and the maximum, etc., etc. And here I mentioned it what we have used. And here there is another episode which happened in my life. This is a meeting with David Dong, the recipient of Gauss Prize of the International Mathematical Union. It was in Rio de Janeiro, a city I love. I spent there quite a long time. And he knew about our result, and even he mentioned that some results he has done it with another guy at Gene and some other people can be improved by using our better bound. So this is our better bound, which is fun. Now about the Wiener process or Brownian motion. So it is not possible to work and to be around Albert Shiryaev and not to do anything with the Brownian motion. And of course, we knew this, and maybe some 20, 30 excellent exercises of our seminar. And then maybe later, I don't know how, but the question came to my mind to ask the following. We keep the normality of the increments, but we want to require the independence only for a finite number of increments. We don't know what will happen for a larger. Maybe they will be dependent. And so my conjecture and my belief was that the answer is no, it cannot be done. And I included this as a conjecture in the very first edition of my book. So it was 1987. And meanwhile, I had another interesting conversations with Richard Dudley, who died a few years ago. So we met in Vilnius at 85, and then we continued at MIT in his office. And he found that this, to put together all these results makes a very good and very attractive picture. Especially he liked this, that WT power 3 is non-unique. However, you take the absolute value, it becoming unique. But the most interesting was that our discussion was in Russian. He knew, I would say, modestly, well, the language, Russian. However, he was so enthusiastic, so he used the Russian all the time and on any occasion. But then we went to his students, and of course, we switched to English, and then I formulated also this conjecture that we cannot characterize the Brownian motion by normality of the increments only in finite, up to finite fixed number. And okay, this is the reaction of. So what happened next? Because the clock is ticking, so there was no progress, but there were attempts to prove or disprove, and I repeated the conjecture in the second edition of my book, 10 years later. And meanwhile, our very respected colleagues at Mark Yor and Hans Fjellmer, they found that this conjecture is challenging, so they worked on this, and they prepared a paper, which I think Mark Yor presented at the European Congress of Mathematicians, of Mathematics, in Barcelona, 2000. And they, somebody told me that the main point in the paper and talk was proof of Stoyanov's conjecture. Of course, they went much further, and they published a long paper under this title, With Brownian Motion of Arbitrary Order K. So they developed some properties, constructed stochastic integrals, equations, including applications in stochastic financial models. And I was in a good position in the third edition of my book to write exactly in 2 lines that in this year, so these authors, they did what is expected. Now, random sequence whose limit is not normal. Now we use cumulants in parallel with moments. So I don't have, I have given talks on the cumulants and maybe even a part of this result. And I will go directly to the model. So now this is the question. So if we have a sequence of independent bounded, so all moments value, so we have this, we write this, and we are asking, does the central limit theorem hold? And sometimes yes, sometimes no. And if no, I remember well, one of the advice of Albert Chiraev to me and to us, that if the limit of some sequence, random sequence, is not normal, try to explain to yourself and to others why and what the reason. And now we know the reason in this case. So we have the model, we have a discrete, uniform random variable, and then we have this probability distribution. And in this case, it turns out that the limit which somebody may expect will be the normal, it turns out it is a bounded interval, strangely enough, between -3 and 3. And even we have the explicit description of the limiting random variable z. It is an infinite sum of, and here we have the exact description. So decreasing linear combination of uniform continuous on the same interval -3, 3. So the reason of this to happen is explained here, the contribution. So there is no Lindeberg condition, there is no this U1, uniform asymptotic negligibility condition. So because of this, we have a limit at which is not the normal, which is not normal. And then there is something else, a little bit more general. I'm looking at the time, and there is okay, let me, this is the very last part. Now, suppose we have a family of different distributions, and there is one we like very much, F0, because we know some properties of F0. And then we want to compare the others with F0. And I refer here to a recent paper by the authors, Sun. It's statistical papers. And I will give the statement, it is below, in my own words. So we have random variable x. So this is what we want. We want to compare, do you see now I'm showing it this, so this is the probability we are interested in. It's a kind of concentration, how much values of which part of the mass of x is around the mean value, on the left, on the right. And of course, I'm writing here T1, 2, 3, remembering the classical case with the normal when we know everything. Surely there is no problem to do this with any other distribution. Now, what they showed is that for arbitrary parameters of x, we have a strong inequality. So what I'm showing now, so this is strictly more than this. And here is one possible interpretation, that x is more concentrated than z. If it is less, then x is less concentrated than z. And here is the result that by specifying only the log normal, because we like very much at this, okay, I'm talking about Dong, me, and me, we like very much the log normal distribution and the inverse Gaussian. And it turns out that we have the strong inequality here for arbitrary log normal, any parameters. However, the infimum of this quantity is exactly equal to this, which is quite interesting. And we have similar for the IG in inverse Gaussian with any. And also what they established, okay, they found that when we attained for which values of mu and sigma square and which mu and lambda, we have this equality. And then we have the chance to interpret this and to talk about some other properties, including the infinite divisibility property of X. And what we have here is, for example, Ig is infinitely divisible and M dead. Log n is infinitely divisible and M in dead. However, it turns out they have very similar concentration property. And we can ask a similar question when not 1 sigma, but when we take 2 sigma, and here 2, this one is the variance of the deviation of Z, and then 3 times, probably it will work. So I see my time is over, and you can read it, but thanks everybody. And so I will stop here, now our boss, Lena.
Thank you so much, Jordan, for your perfect talk. And dear colleagues, now we have time to discuss for this talk. Maybe you have some comments or questions, please.
Hi, can I ask?
Of course.
Hello, everyone. My name is Carlos Pacheco from Mexico City. I am actually former student of Yordan Stoyanov. I'm very happy to be here to say hello to Yordan in quite some time. Thank you, Yordan.
Mm-hmm,
And
okay.
and I want to ask you something, because you have these very nice stories about basically history about this moment determinacy problem, which is quite a long story, and you say many interesting things. But I suppose once we work on this problem, moment determinacy, there is also the so-called inverse problem in areas of statistics, of probability, even in analysis in general, when people have some moments, maybe in the form of spectral information or something, and people want to recover something of a model, maybe some probability, maybe some function. And I suppose there is also a long story about the inverse problem regarding moments. What do you think about that?
Okay, of course, I think very positively to get the question. I'm very well aware and familiar with the studies in this area, but this is another topic. We don't have time because I spoke in almost 60 minutes, but you are absolutely right. And these inverse problems, they are quite serious, and they have good applications. Maybe someday we will discuss it, maybe when meeting in Mexico City.
Right, okay, thank you. Well, I want just very quickly to say hello to Professor Albert Turgev. I know it's his 90th birthday, and I'm very happy to hear that. When I was a student with Jordan, I went to Lisbon, Portugal, to celebrate his birthday. So it's very nice to say happy birthday to Professor Turgev. Bye-bye.
Okay.
Dear colleagues, in other comments, please. Today we have great experts in moment problem, Professor Stoyanov and Professor Lin. Please, your comment. Maybe you have some comments, questions, please. And I would like to ask, maybe it's a naive question, but I'm interested in such problem. We know about the necessary and sufficient condition of M determinants of random variables in terms of Hankel matrix.
Yes.
And of course, we know very general Karleman condition, very general sufficient Karleman condition. And could we have another sufficient condition more general than Karleman? or not, or it is open?
Probably not. I can answer. I can answer immediately. It seems that the answer is not, because there is a statement telling that the Kalman condition is the best possible sufficient condition for the moment uniqueness or moment determinacy. And the other, you mentioned this Kahneman, some eigenvalues, minimal, etc. Look, all these conditions, they exist. It is a very hard mathematics, very beautiful, but it is uncheckable. Nobody can check these conditions. However, everybody can check our conditions, the conditions we like, the conditions we worked on, the conditions we are speaking of, and the conditions we are writing in our papers, etc., etc. And this is what people in applications like.
Thank you. So, as I understand, really, your answer, it is open questions on this time, yeah? But of course, I agree with you that it is a difficult, I think, problems. Maybe another comments. Dear colleagues, friends, please another comments. Maybe Albert Nikolaevich, are you with us? Maybe you would like to speak some words or not. Today, I think we have not so good connections, internet connections. I don't know, maybe Albert Shiryaev with us or not. So in any case, I would like
Lena, I think that there are people attending online, and they contacted me and they asked me about the possibility for them to tell a few words. Okay, ask again among the somebody from the attendees, участников, somebody wants to tell a few words.
Hello, may I ask? May I tell something?
Yeah, of course.
Lena, yeah.
Okay, hello, greetings to you all. I am Dusan Georgievich, and I am a part of a group in probability and stochastic processes in Niš in Serbia. And of course, first of all, we wish to congratulate to Professor Shiryaev for all the accomplishments and the influence that he has in the field all over the globe. We haven't had a direct contact with him, but Professor Yordan Stoyanov had some really significant work with our professor Svetlana Jankovic, which at the time nobody in former Yugoslavia did those kinds of works in the fields of stochastic processes and stochastic differential equations. So Professor Svetlana Jankovic will soon have 14 direct academic descendants, which are, of course, descendants of Professor Stoyanov and Professor Shiryaev. So I want to thank both of the Professor Stoyanov and, of course, Professor Shiryaev once again for everything that he has done. And we wish him all the best for his birthday. That's all.
Yeah.
Okay,
thank you
Albert,
for your...
Lena, what about Albert?
He's here with us, but without sound connection and camera connection.
I can tell you the internet connection is unstable.
Yes. And
I'm getting this on my screen already 5 times.
In any case, today we made a record of your lecture, and I think 1 week later everybody can hear it on a site of our seminar. And in conclusion with it, with our seminar, I would like to say some words about our problem and about some exchanges. As I told, we thank Vladimir Putsenko, our previous secretary of seminar, and now the secretary of seminar, Oleg Ivlev, and you can write about your wish to give a talk to me or to Oleg Ivlev. And now I would like to say some words about our next seminar. It will be a talk of Abeldaev, Timirlan Abeldaev from St. Petersburg Mathematical Institute. And the title of his talk, generator of symmetric Levy process, and connecting with it limit theorem. So we wait all of you on our next seminar. Thank you, everybody.
Sorry.
And
can I just interrupt?
yeah,
Sorry, I also wanted to congratulate Albert. So if I can do it very quickly now or maybe later. So first,
I would like to say
Sure, go ahead.
our leader, Albert Nikolaevich Shiryaev, decided that in frame of our seminar, of course, I think he is very glad to see everybody, but he prefer to discuss only scientific problems in frame of our seminar. Thank you once more for everybody for their warm greetings and so on. Maybe, colleagues, I repeat the talk of the seminar in Russian. Значит, в следующую среду выступает Абельдаев Тимирлан из ПАМИ Санкт-Петербургского, и название его доклада «Генератор симметричного процесса Леви с дельта-потенциалом и связанные с ним предельные теоремы». Ждем вас всех на следующий семинар. Еще раз спасибо нашему блестящему докладчику профессору Стоянову, и рады вас всех видеть на наших семинарах.
Okay.
Всего доброго, и мы завершаем.
Okay. Bye-bye. Thank you, Lena, for guiding
Спасибо.
so well. Okay. This meeting will be recorded.
Да, всего доброго. Все, ждем вас.
Спасибо.
Всего хорошего.
Let's see.
Олег, да, все, спасибо всем, и мы завершаем.